Hello and welcome to this section of the Calculus Derivative Help Tutor. And in the last section we introduced the chain rule. So we talked about the fact that to apply that you have to have an outer function with an inner function sort of nested. And this nesting can continue to go as deep as you want. Of course your derivative will be more complicated, but there's no limit to how many layers you could put. But on a typical test you'll have 2 layers or maybe 3 layers maximum, because beyond that it just gets to be really ugly to deal with. So we've gotten some good practice on how to do the fundamentals. Here what we're going to do is work some additional problems, slightly more complicated, but I really want you to understand that there's really nothing fundamentally harder about it. It's just really the algebra. I think I've shown you through this point, calculus is not hard. The rules of calculus is not hard. It's the algebra that becomes a bear when you have all the simplification to do. So you really have to be strong in that. So what we're going to do is do some challenging problems indicative of what you might see on your test. And if you guys can do these, and the extra ones that you can find in your book, in your textbook, you'll be absolutely fine and comfortable dealing with the chain rule. So let's say we had a function f of x is equal to x times the square root of 2 minus 7x squared. All right? So notice here that this is immediately more complicated for 2 reasons. One, we know we have a nesting going on because we have a square root function, and inside of that guy is another function. So that's more complicated. But to make it even harder, on the outside of this we have another function, x. So a lot of students might look at this and really don't know where to start, but you have to peel back the onion. First thing I always tell people to do is always rewrite these functions with radicals as the following in this case: 2 minus 7x squared to the 1/2. This is much easier to read, even though you have a fractional exponent, because here you know you have an exponent here, so you're going to be using your exponent rule. The inner function is fairly easy to deal with in this case. The only real wrench is that you have this guy out here. All right? What you need to realize is that ultimately, at the big picture point of view, you have 2 broad functions here. You have this function multiplied by this large function. What do we do when we have 2 functions multiplied by one another? We use the product rule. We've done the product rule over and over. It's just that this second function is kind of ugly. We're going to end up using the chain rule on this part of it here because we have a nesting. But don't forget the larger part is the product rule that we have going on here. So that's what we're going to do. We're going to use the product rule as the outermost thing because that's really what's going on here. So what's the product rule? It's the first function times the derivative of the second function plus the second function times the derivative of the first function. So let's go and do that. It's the first function times the derivative of the second function. So we'll have 2 minus 7x squared raised to the 1/2 power. First times the derivative of the second function, that's what this means, plus the second function, 2 minus 7x squared raised to the 1/2, times the derivative of the first function over here, right there. Notice I haven't taken any derivatives yet, because if you start trying to do it all in one step, first times the derivative of the second. If I started trying to take this derivative on top of everything else early on in your study of calculus, you're just going to make a mistake. So write it out like this. And then in the next step, it's very simple. Well, simple is not the right word, but it's much more straightforward to go in here and say, okay, I have this x. Now how do I handle this derivative? Tackle that guy. When I get over here, how do I handle this derivative? Well, when we're here, we have this nested function going on, so we have to use the chain rule. So what you're going to have, the outer function is this exponent. So you'll have 1/2. The inner guy is going to stay the same, just like we've been doing in the other problems. We subtract 1 off the exponent, and we're going to get negative 1/2. But we can't stop there because we have to multiply by the derivative of the inside. Now this is simple enough where I'm just going to take the derivative right here. The derivative of 2 is 0. The derivative of this, 2 times 7 is 14. We have a negative, so it's negative 14x. Right? So this is the derivative of this whole term is what we have here. We have the outer guy with subtracting the exponent times the derivative of what we have in the middle. So we're done with that. All right? And then after we do that, we're going to have over here plus 2 minus 7x squared to the 1/2. What's the derivative of x? Well, it's just 1. So that's very, very simple at the end. Okay? All right. So what we need to do here is combine everything that we have here. So we'll have f prime of x, let me get a better marker here, f prime of x is equal to 14 divided by 2 is 7. We have a negative here, so we'll have negative 7 x times x gives me x squared. And then we have this guy, 2 minus 7x squared to the negative 1/2. Okay? And then over here we have 2 minus 7x squared to the positive 1/2. So we have is negative 7x squared, 2 minus 7x squared to the negative 1/2 plus 2 minus 7x squared to the positive 1/2. Now, truth be told, this is the answer. I mean, it really is. But just like in this course, I'm trying to teach you your algebra skills at the same time, there is a way to simplify this that your teacher might like to see a little bit more. So let's go ahead and get some practice with that. Let's rewrite everything. Negative 7x squared. On the bottom, we're going to have 2 minus 7x squared to the positive 1/2. All I did was take this whole term and move it down. Over here, you're going to have 2 minus 7x squared to the 1/2 over 1, because this is always over 1, right? Now what we have is two nice terms we would like to add together, so we have to try to find a common denominator. The easiest way to do that is to multiply this by this guy, 2 minus 7x squared to the 1/2. If we multiply it on the bottom, we have to multiply it on the top. Right? So we only do this so that we can get a common denominator across both sides. But a nice thing happens once we do it. We have f prime of x. All right? On the top, what are we going to have? We have negative 7x squared over 2 minus 7x squared to the power of 1/2. And then over here on the right-hand side, we have this multiplied by this, but notice the bases are exactly the same, so we just add the exponents. So 1/2 plus 1/2 is 1, so all you'll have is on top is 2 minus 7x squared. And on the bottom, 1 times this is going to give us what we wanted to get, 2 minus 7x squared raised to the power of 1/2. So we have a common denominator, which is the only reason we did that. So let's go ahead and add these two fractions, f prime of x. Notice that when we add this to this, we have 7x squared and negative 7x squared. So what we're going to have is, let's put the 2 out in front, minus 14x squared, because these are simply added together. On the bottom, we keep the same common denominator, 2 minus 7x squared to the 1/2. Now you could write the bottom as a radical if you prefer, but ultimately this is the answer. So this is pretty significantly more simplified than what we have up here. But this is the derivative. You could leave it just like that. But anytime you see terms with such a common theme to them, it's probably a good idea to spend a minute to see if you can simplify them at all. So we just find a common denominator. Once we do this, it drastically simplifies the numerator. The denominator stays the same. 2 minus 14x squared over what amounts to the square root of 2 minus 7x squared. But ultimately, it's the same process. We take the derivatives using the rules that we know. If we get to a derivative that's nested, then we end up using the chain rule, which is just another tool in your tool bag. All right, what if we have f of t is equal to sine to the 4th power of t plus cosine to the 4th power of t? All right, so I usually recommend, at least in the beginning, that students rewrite these things. I mean, I'm comfortable with it, but at the beginning you may not be. So just think of it this way, sine of t to the 4th power plus cosine of t to the 4th power. Because that allows you to see a little more easily, okay, I have an exponent with a nested guy on the inside. So f prime of t is equal to, what is the derivative of the first term? Well, the outer is raised to the 4th power, so it's 4 times the sine of t to the 3rd power, but we have to multiply by the derivative of the inside, which is cosine of t. Derivative of sine is cosine. So that's the first term. Then we add to that, here, this 4 comes down, same as the other one did, cosine of t raised to the 3rd power, but we multiply by the derivative of the inside. Derivative of cosine, negative sine of t. That is the answer. We'll clean it up just a little bit, just kind of like good math manners, we'll try. So what we have is 4 times cosine t times the sine cubed of t. We'll rewrite it like this. This is how you'll see it in the textbook. Here we have a minus sign, so it will be minus 4 times the sine of t times the cosine cubed of t, cosine cubed of t. And that's what we have right there. 4 cosine sine cubed t minus 4 sine cosine cubed t. So you see, even though it's kind of ugly, you think, oh, these fourth powers are going to be really ugly and nasty. It's not that bad, people, because really, you just have to take it one step at a time. We take the derivative of the first term. We take the derivative of the second term. It just so happens that each of those terms are nested. So we have to apply the chain rule to each one of them, which, once you get more and more comfortable, becomes more and more mechanical. So let's say we have a different function, f of x, I should say, is equal to the square root of x squared plus 1 over x squared. Right? So here we're getting a little bit gradually uglier and uglier, so to speak. But let me give you a hint. First of all, convert these radicals to powers. Second of all, when I have a fraction like this, especially wrapped up, I like to change that around too. So the way I do it is x squared plus x to the negative 2, all raised to the 1/2 power. Now I'm going to tell you now, this isn't very pretty either, but I don't like to look at radicals, and I don't like to look at fractions unless I really have to. So here I have exponent, exponent, exponent. It's always easier to deal with exponents than it is to deal with fractions or radicals. That's sort of like my philosophy. So I change it around. And then when we take this derivative, the outer function is this giant exponential. The inner function is what we have there. So taking the outer guy first, we'll have 1/2 times, leave the inside intact. 1/2 minus 1 is negative 1/2. And then we have to multiply by the derivative of the inside. But this is easy now that these are straight exponents. So we'll have 2x from this guy. And then over here, we'll have minus 2x to the minus 3 for the second one. The second one comes, the minus 2 comes down. That's where this comes from. X to the minus 3 because we're subtracting 1 off. So this is a straight derivative that you know how to take very, very simply. If you left it like this, you can do it as a quotient rule, but it's just going to make yourself, make your paper not as nice. So in order to make any progress, let's just sort of rewrite what we have. F prime of x is equal to, on the top, see this is going to end up going to the bottom. On the top we're going to have all this stuff. So we'll have 2x minus 2 over x cubed. I could leave it as an exponent like this, but I'm just trying to get it back into a form that the book gave us to. This 2 is coming to the bottom because it's a fraction. This guy is x squared plus 1 over x squared, and this is going to be to the 1/2 power. So we're taking this guy, making it positive by bringing him to the bottom, right? And this 2 comes down because it's the fraction, and then this stuff just stays in the top, written like this. Now notice, I'm not going to show the factoring step, but I think you'd agree. You can factor out a 2, you can factor out a 2 on the top. You can factor out a 2 on the bottom. Those are going to cancel. So ultimately, this 2 cancels with these, like this. So ultimately, putting it in final form, the derivative is x minus 1 over x cubed on the top over the square root of x squared plus 1 over x squared. X minus 1 over x cubed on the top over square root of x squared plus 1 over x squared. That is the derivative. Now, you had the answer way up, essentially you had the answer here. This is the answer. So if you're crunched for time on a test and you have like 5 minutes left, just leave it like this. But certainly it's good math skills and all that stuff to get your full credit to go ahead and try to put it down and try to do some cancellations, right? So don't get scared of radicals. I know when I started, I was worried about radicals. It made things harder. Don't be worried about quotients. Sometimes use the quotient rule, that's easier. Sometimes it's better to write it as a negative exponent, and then that's easier, right? So we're trying to get some experience with that. What if we have f of x is equal to 1 over x times the square root of 5 minus 2x. All right. So again, don't leave yourself hanging with these guys. Now, in fact, in this case, there's an even easier way to rewrite this function before we get started. This is how I would recommend doing it. X to the negative 1 times 5 minus 2x to the negative 1/2. Make sure you agree that this function is the same as the other one. I don't have to do this. I mean, I could have rewritten it exactly like this, but on the bottom with a exponent. But then you would have to use the quotient rule. And the quotient rule is nice and easy in some situations, but in some situations it just makes it too much stuff to deal with. The quotient rule is going to give you exactly the same answer as doing it this way. It's just that, you know, bottom times the derivative of the top minus the top times, it's just more stuff to deal with sometimes. So when you can, write it all up on one line, and you're going to still have to use the product rule here. You have this function times this function, but in my opinion, it makes it a little bit easier to handle. So product rule, this times this, right? So what are we going to have? F prime of x. First times the derivative of the second, 5 minus 2x, negative 1/2. So first times the derivative of the second plus the second times the derivative of the first. I haven't taken any derivatives yet on purpose because this derivative is going to be a chain rule. I have an exponent, but I also have something in the middle. So let's deal with this guy. I'll have x to the negative 1 on the inside here. I'll bring this negative 1/2 down. 5 minus 2x. What is 1/2 minus 1? If you think about it, 1/2 minus 1 is negative 3/2. But I have to multiply by the derivative of the inside. The derivative of this is 0. The derivative of this is negative 2. So that closes off this derivative here. This was the chain rule. I used the chain rule for this part of it. But then here I have 5 minus 2x to the negative 1/2. And then here, what is the derivative of this? It's negative x to the negative 2. Take the negative 1 down, subtract 1 off the exponent. All right, so that is essentially the answer. If you we're going to just stop right there. If you had 5 minutes left in your test, that's the answer. But notice that we can simplify. We have a 2 and we have a 2 on the bottom, plus, and we have a negative and a negative. So this negative 2 is going to cancel with this negative 1/2. That's going to be gone. All right. And so when we get around to rewriting it, what we're going to have is f prime of x. What we're going to have is 1 over, for this first term, this x is going to come down to the bottom. This is going to come down to the bottom. 5 minus 2x to the positive 3/2 because we moved it down to the bottom. This cancellation removes all of that. Over here on the second guy, we're going to have a negative from this, right? And then we're going to have 1 over. This x squared is going to come out in front. And then this 5 minus 2x to the positive 1/2. That is going to be the answer right there. So we'll have 1 over x, 5 minus 2x to the power of 3/2 on the bottom, minus 1 over x squared, 5 minus 2/2 to the, or 5 minus 2x to the power of 1/2. So it's the same exact thing. You have to look at the big picture first. Rewrite it. First times the derivative of the second plus the second times the derivative of the first. But then we noticed when we take this derivative, we have to use the chain rule. So we use it when we need it, right? And we get the answer and then we simplify down. We could put radicals here if we like, but there's no point to really getting to that level of detail. And the other thing is, if you wanted to do the quotient rule here, you could. It's just it's really up to you. It's a good exercise. Do the quotient rule on this. You'll get exactly the same answer. It's just because you have the bottom squared and all that stuff, bottom times derivative of top minus top times derivative of bottom, bottom squared, and then you'll have other derivatives mixed in there. It's a little bit harder to simplify it, in my opinion, in some problems. But you will definitely get the answer, the exact same answer, doing it either way. Okay, for our next problem, we're going to have our function f of x is equal to x times cosine of 1 over x. So again, looks a little bit ugly at first, but I always recommend that you rewrite these fractions, especially when they're nested, as exponents. So this is the same function as x times cosine of x to the power of negative 1 on the inside. Okay? But notice the big picture. You have a function x times this function. So you have two functions multiplied together, this cosine function, times this guy. So we're going to use the product rule right out of the gate. So f prime of x is equal to first times the derivative of the second, cosine of x to the negative 1, first times the derivative of the second plus the second, cosine of x to the negative 1, times the derivative of the first. First times the derivative of the second function plus the second function times the derivative of the first. I've taken no derivatives yet. F prime of x is equal to x what is the derivative of cosine? Because this is a nested function, this is where we're going to have to use the chain rule. We have an outer function and an inner function. So the derivative of cosine, the outer function, is negative sine. We keep the argument intact, but then we take the derivative of the inner guy, which is negative 1 times x to the negative 2. Take the exponent down, subtract 1 off the exponent. All right? And then for the second part over here, we're going to have cosine of x to the negative 1 multiplied by the derivative of this guy, which is just 1. So we just use the chain rule when we need to. In this case, we had to use it in turn in taking it as part of the product rule that we were using to begin with. Okay, so what we're going to have is just multiplying it all out. Negative times negative is going to give us a positive, right? So we're going to have positive. This guy is going to be out here. So what we're going to really have, negative times negative is going to give us positive. And if we look here, we have an x times an x to the negative 2. So really what we're going to have is adding these exponents. So x to the negative 1 times the sine of x to the negative 1. The negatives cancel with this guy. These guys, we add the exponents. So we have x to the negative 1 plus cosine x to the negative 1. And really that's the answer, but if we want to just sort of tidy it up, what we'll have is sine of 1 over x. This guy comes down to the bottom, we change the inside, plus cosine of 1 over x. And that's the answer. Sine of 1 over x plus cosine of 1 over x. All right, our next problem is g of z, so just change variables, but it's the same deal. Cosine squared of 3z to the power of 6. All right? So we have an outer function and an inner function, but to make it a little more clear, I usually in the beginning recommend for students to write these things. Cosine of 3z to the 6, write it as like this. So write this exponent wrapping around everything. That way you can more easily see, okay, the outer function is this exponent. The inner function is the cosine. All right, but I want to also bring something else to your attention. Notice that this is actually one extra layer. The outer function is the giant exponent. The inner function is the cosine of this guy. But then we have another function on the inside, which is 3z to the 6th. So we actually sort of have like 3 layers here. So this is going to be a problem where we're going to be continuing to multiply on the inside using the chain rule. But it's not really any harder. It's just something you have to learn. So let's go ahead and do that. So what we'll have is g prime of z is equal to. The outer function is this 2, this exponent. So we'll bring the 2 down. We'll keep everything in the center. Cosine 3z to the 6. Everything in the inside stays the same to the power of 1. I'll just write it there to be explicit. We can't stop there. We have to multiply by the derivative of the inside. We've done problems like this already. This itself requires the chain rule because we have an outer function, a cosine, an inner function, which is something other than, z. So we have to say, what is the derivative of cosine? It's the outer function here. It's negative sine. Negative sine, we have to keep the inside exactly the same, 3z to the 6th power. But we can't stop there because we haven't even touched what's on the inside. So we have to multiply by the derivative of the inside. 3 times 6 is 18z to the 5. Make sure you understand. There's 3 layers here. The outer guy is this exponent. We leave everything the same on the inside. Then we take the derivative of the inside, this guy. That is what this is. All right? So we take the derivative of this, derivative of cosine is negative sine, inside stays the same. But then, for the final step, we have to take the derivative of purely the inside. So we basically keep multiplying in the chain rule, inner and inner and inner, taking derivatives as we go to get to the answer. So just to tidy this up, g prime of z is going to be equal to 2 times 18 is 36. We have a negative sign, so negative 36 cosine of 3z to the 6th power times the sine of 3z to the 6th power. And don't forget we have the z to the 5th sitting out here, z to the 5th. So we'll have negative 36 cosine 3z to the 6th times sine 3z to the 6th times z to the 5th. Right? So this is a great example of having multiple nested layers in a chain rule And the same exact process goes. You start outer, work inner, until you basically run out of things to take the derivative of. All right? So let's go ahead and do the next guy. Let's say we have f of x is equal to the cotangent squared of 2 times the radical of 3x plus 1. All right? So I always recommend, again, to rewrite these things, especially in the beginning. So what you'll have is cotangent of 2 times 3x plus 1 to the 1/2 power, right? Let's go ahead and wrap all of this stuff in a bracket and raise it to the power of 2. That's really what we have. And the reason we write it like this is because it's much easier to see. It's like, okay, the outer function is this exponent. Then we have an inner function that's a cotangent, but the argument of the cotangent is yet another function. So again, we have 3 layers. So we're going to basically keep taking derivatives and multiplying as we go in. It's just a matter of keeping it straight, though. So what we'll have is f prime of x is, first work with the outer guy. The 2 will come down, then you will have cotangent of 2 times 3x plus 1 to the 1/2 power. Okay, that's the outermost layer of the onion. Then we have to multiply by the derivative of the inside here, the entire cotangent. What's the derivative of cotangent? It's negative cosecant squared. So what you'll have is negative cosecant squared of the inner guy, which is 2 times 3x plus 1 to the 1/2. This is just simply the derivative of the cotangent, so we leave the inside alone, but then we have to multiply by the derivative of the inside, right? So what you'll have is 2 times, let's write it like this, 2 times the 1/2 comes down, right? And then we have 3x plus 1 minus 1 there gives us negative 1/2. But we're still not done because we have to, let me go ahead and write it like this, because we have to multiply by the derivative of the inside here, which is just 3, because this is 0. So the derivative of this is 3. The derivative of this is 0. Make sure you truly understand what's going on here. What we have is the outer function's this square. So we have 2, everything on the inside, raised to the 1 power. Then we multiply by the derivative of the inside, which is everything here. Derivative of cotangent's negative cosecant squared. So we have this with everything wrapped up inside. Then we have to take the derivative of the inside of here. So we say 2 times the 1/2 comes down, this to the negative 1/2. But again, we're using the chain rule again because here we have this, but we still have this inner function. We have to take the derivative again, giving us the 3. So we actually have more than, when you think about it, we really have like more than 3 layers. We almost have like 4 layers. The first layer is the square, then the cotangent, and then this function has a radical with something kind of complicated wrapped inside of it, so it's almost like 4 layers. All right, so when you actually get around to writing this down in a little bit pretty manner, what you're going to have is everything's multiplied together. So 2 times 3 is 6, but you have a negative sign here, so what you're going to have is negative 6. Then you're going to have this cotangent function, cotangent. And on the inside, you'll have 2, and then let's convert this back to a radical, 3x plus 1. That takes care of all of this, right? Just don't forget the cosecant squared. So what we'll have is cosecant, let's do it, cosecant squared of what we have on the inside, 2 times the radical of 3x plus 1, like this. And then what we have down for the final term, the 2's cancel like this, so that doesn't really matter. So everything here, the 3 is already taken care of. This is negative, so what I'm going to do is draw a nice fraction bar and bring this down below and make it a square root 3x plus 1. Negative 6 cotangent with that argument times cosecant squared of that same argument over square root of 3x plus 1. Very, very ugly problem. The reason that it's that way is because you have so many nested functions. The square, the cotangent, and then the inner guy is a radical with something else on the inside. So every step of the way, basically what you're doing is multiplying by the inner function's derivative over and over and over again. So I think we've done enough problems to give you a good feel for how to handle the chain rule in calculus. I could give you a million more problems, but all it's going to boil down to is looking at the big picture. What is the largest, broadest rule I need to apply? Is it the product rule or is it the chain rule? apply that rule, write down your derivative. When I see that I'm trying to take the derivative of a function that's nested, then I need to apply the chain rule. And hopefully giving you this gradual increase in difficulty of examples hopefully has given you some important skills and some confidence. But I encourage you to watch this lesson again, work these problems again, make sure that you really do understand how to do this, and work a ton of extra problems in your textbook. There should be lots of extra odd number problems in your textbook that you can work to get your skills down. A lot of it is algebraic, really. The derivative part does get a little complicated with really nested functions. Most of it's algebraic simplification. I'm Jason with MathTutorDVD.com. Watch this section as many times as needed. I guarantee you will have tons of questions on your test with the chain rule, and you'll be using the chain rule all throughout Calculus 1, 2, 3, in almost every math class you take, an engineering class and science class that you take in your study of your future courses.